August 12, 1945. The Pacific War has burned for 1,344 days. The Imperial Japanese Navy has largely ceased to exist as a coordinated fighting force. The atomic bombs have already fallen on Hiroshima and Nagasaki. The United States Navy is sitting at anchor in Buckner Bay off Okinawa, waiting for word from the highest channels that the end is coming, that Japan will soon accept unconditional surrender. The heavy units of the fleet are resting. The mood is one of exhausted anticipation. At 8:45 in the evening, a single Japanese torpedo bomber drops out of the fading light. It is alone, unescorted, and low, threading a gap no one is watching. It releases one aerial torpedo. The weapon runs shallow and true. It bypasses the screen of destroyers and strikes the massive hull of the USS Pennsylvania. The explosion tears through the steel plating on the starboard side. This impact creates a dark historical paradox. The Pennsylvania is one of the last major United States warships to take a serious hit in the Second World War. She is a vessel that defines the entire conflict from the first second to the last. She is the bookend battleship. To understand the specific cruelty of this torpedo strike, you must understand where she began. On December 7, 1941, the Pennsylvania was not in the mud of Battleship Row. She was sitting in dry dock number 1 at the Pearl Harbor Navy Yard. She was the fleet flagship. She shared the basin with 2 destroyers, the Cassine and the Downs. This position saved her from the aerial torpedoes that ripped into Battleship Row and from the bombs that detonated the forward magazines of her sister ship, the USS Arizona. She was protected by the physical architecture of the naval base. The critical component of her survival in 1941 was the dry dock caisson. A caisson is a massive floating steel gate that serves as a movable dam. Engineers ballast the caisson with water until it sinks into a dedicated seat at the entrance of the dock. This creates a watertight seal against the harbor. When the dry dock pumps evacuate the water from the basin, the immense pressure of the outside ocean forces the caisson tighter against its seat. Inside this concrete shell, the laws of buoyancy are suspended. During the attack on Pearl Harbor, the caisson held. The destroyers ahead of the Pennsylvania were destroyed by fire and bomb hits. The Pennsylvania took strafing, flying debris, and the ugly randomness of metal in motion, a torpedo tube from the Downs blown onto her forecastle. But her hull remained watertight. She was battered and shaken, yet she could be made ready again. After repairs and rework, she left the dock and rejoined the war. She bombarded the Aleutians and the Philippines. She would probably fire more ammunition than any other heavy ship in the fleet. She moved steadily west across the ocean for 4 years. By August 1945, the safety of the dry dock is 4,000 miles away. The Pennsylvania is exposed. When the torpedo strikes on the 12th of August, it ignores the heavy armor belt protecting the center of the ship. The torpedo finds the vulnerable stern. The warhead detonates well aft of the main citadel. The blast energy does not encounter the thick steel designed to deflect heavy shells. It encounters the thinner shell plating of the steering compartments and the officers' quarters. The shockwave propagates through the internal voids. 20 men are killed, 10 others are wounded. These sailors are among the last combat deaths aboard a United States battleship in the war. They die while the rest of the fleet is preparing for victory celebrations. The ship immediately shudders. The blast has opened the hull to the sea. On the bridge, the officers are not yet thinking about the structural physics of the stern. They are reacting to the violation of the peace. The enemy has no carriers. The enemy has no fuel. Yet a single plane has still landed a crippling blow on the very eve of surrender. The Pennsylvania is now the last victim of the conflict. The crew rushes to general quarters, but the damage is already done. The ocean is entering the hull, and the war is not over for this ship. The decision to recover her will not be based on combat necessity, but on a refusal to let the last hit be a fatal one. The ocean does not attack a battleship with emotion, it attacks with geometry. In the minutes following the explosion, the crew of the Pennsylvania is not fighting a fire. They are fighting an angle. The stern of the ship is settling rapidly into the Pacific. The waterline, which is usually a fixed constant, has become a dynamic threat moving vertically up the side of the hull. The damage is catastrophic. The torpedo has deleted a massive section of the starboard quarter. The hole is approximately 30 feet in diameter. It is an open wound that exposes the intricate internal anatomy of the ship to the sea. The blast has destroyed the steering gear room instantly. The rudder is jammed. But the more critical threat involves the propulsion tunnels. Naval architects designed battleships around the concept of the shaft alley. A shaft alley is a long, watertight corridor that houses the massive steel propeller shafts connecting the engine rooms amidships to the screws at the stern. It is a necessary structural void. It allows engineers to access the bearings and lubricate the drivetrain. But in a flooding event, a shaft alley acts as a high-volume pipe. If the stern end of the alley is breached, the ocean can rush forward along the length of the shaft, bypassing transverse bulkheads and flooding the engineering spaces deep inside the citadel. On the Pennsylvania, the water surges into these alleys. The ship begins to pivot around her center of gravity. This is a crisis of hydrostatic trim. A ship floats because the force of buoyancy pushing up equals the force of gravity pulling down. Under normal conditions, these forces are balanced along the longitudinal axis. The ship sits level. When the stern floods, the center of gravity shifts aft. The buoyancy at the stern is lost. The lever arm takes effect. The heavy stern drops and the bow rises. This creates a dangerous feedback loop. As the stern sinks lower, it submerges hull sections that were never meant to live underwater. On a ship of this vintage, the secondary battery casemates sit close to the sea. If the trim grows too steep, the ocean will start using those gun ports as doors. Once water's on the main deck, watertight integrity stops mattering. The ship will capsize. The damage control parties work in the darkness of the lower decks. They cannot patch a 30-foot hole while the ship is in open water. The physics do not allow it. Instead, they fight to alter the trim. They employ heavy-duty pumps to evacuate the flooding where possible. They counter-flood compartments forward to force the bow down and bring the stern up. It is a calculated exchange of reserve buoyancy for stability. They succeed in arresting the settlement. The water stops rising before it reaches the catastrophic threshold of the main deck casemates. The Pennsylvania is stable. She is no longer sinking. But she is tactically dead. The steering gear is flooded. Both starboard screws are crippled. She cannot maneuver. She cannot retreat. The fleet flagship has been reduced to a 30,000-ton steel raft. The war is ending around her, but she cannot move to the surrender ceremony. She must be taken under tow. The Navy decides to move her to the nearest major repair facility capable of handling a hull of this size. She must go to Guam. The engineers believe the worst of the physics is behind them. They are wrong. They have stabilized the flooding, but they have not yet accounted for the stress of dragging a broken ship across the ocean. Moving a dead battleship across the Pacific Ocean is an exercise in calculated resistance. The tugboat captain faces a relentless trade-off. If he applies too much power, he risks parting the wire or ripping the towing pad eyes out of the deck. If he applies too little, the convoy effectively stands still in the current, vulnerable to weather and drift. This is the constraint of the heavy tow. The Pennsylvania arrives at Guam on September 6, 1945. The war is formally over. The floating dry dock at Guam is one of the few forward facilities capable of receiving her. The engineers assess the damage. They cannot rebuild the internal compartments. There is no time to reconstruct the steering gear or replace the warped bulkheads. The mission is simply to seal the hull for a 5,000-mile journey to the Puget Sound Navy Yard in Washington State. They fabricate a massive steel patch. This is not a delicate surgical repair. It is industrial armor. The workers cut away the jagged edges of the torpedo wound. They weld a steel plate over the breach in the starboard quarter. This plate serves two functions. First, it restores the watertight boundary, keeping the ocean out of the lower decks. Second, and equally important, it restores a fair hull line and cuts the brute resistance of torn metal. A battleship hull is shaped to move through water with minimal disturbance. A 30-foot jagged crater destroys that profile. It acts as a hydro brake, creating turbulence and eddies that grab the water and pull the ship backward. By welding the patch smooth to the hull, the engineers reduce that resistance. The ship becomes safe to move. In October 1945, the Pennsylvania departs Guam. She can move under her own power again, but only at a crawl, and only with help close at hand. Escort ships ride with her, ready to take strain if the sea turns ugly. Even when a battleship is not being pulled every mile, the tow gear still matters. A hawser is not a rigid bar. It is a flexible curve that hangs in the water between ships. This curve is called a catenary. The weight of the wire acts as a shock absorber. When the ocean swells lift the leading ship, the wire straightens slightly, absorbing the energy. When it drops, the wire sags. This constant expansion and contraction manages the tensile load, preventing the sudden spikes in force that snap steel cables. The system works as long as the speed remains low and the sea state remains moderate. For weeks, the convoy moves northeast at a crawl. The patch holds, the pumps maintain the trim, the drag is manageable. The Pacific Ocean seems to be cooperating with the salvage effort. But the damage from the torpedo was not limited to the hull plating. The shockwave had traveled deep into the mechanical spine of the ship. Deep inside the stern, the propeller shafts are sitting idle. During long stretches at slow speed with engines stopped, the water flowing past the propellers can cause them to windmill or rotate slowly. Usually the engineers lock the shafts to prevent this. But on the Pennsylvania, nothing about the drivetrain is usual anymore. On October 17th, the crew feels a new sensation. It is not the rhythmic rolling of the ocean. It is a mechanical shudder, metallic, wrong, starting in the stern and transmitting through the framing. The engineers go below to inspect the shaft alleys and discover that the physics of the tow have triggered a secondary failure. The repair at Guam covered the hole in the skin, but it could not fix the broken bone inside the leg. The vibration in the stern is not a loose fitting, it is the death rattle of number 3 propeller shaft. The situation escalates from a mechanical nuisance to a structural emergency. The shaft does not merely crack, it snaps. The failure mechanism is shear stress. While tensile load pulls a material apart from the ends, shear stress tears it internally by sliding its layers against each other in opposite directions. It is the physics of a pair of scissors cutting through paper. The torpedo impact months ago had likely warped the alignment of the drivetrain. For weeks, the shaft rotated slightly in its bearings, grinding against the distortion. The steel fought the misalignment until it reached its fatigue limit. Then the molecular bonds surrendered. The break occurs inside the stern tube. This creates an immediate physical hazard. A battleship propeller shaft is a massive cylinder of solid steel. It weighs many tons. Without the connection to the engine room, the shaft is no longer held in place. Gravity and the drag of the water begin to pull the heavy propeller aft. The shaft starts to slide out of the ship. This is a nightmare scenario for the salvage team. If it slides all the way out, the stern tube becomes the same threat in a new form, an open invitation for the Pacific. The pumps would be overwhelmed. Alternatively, if the shaft slides out but hangs loosely in the bracket, the massive propeller could swing wildly, smashing the rudder or the remaining screws. The convoy halts in the open ocean. The water depth here is thousands of feet. They are far from any dry dock, and there is nothing overhead that can lift a shaft that weighs tons. The engineers make a decision that seems to violate the basic rules of safety. They will not try to pull the shaft back in. They will cut it loose. They deploy Navy divers into the water. This is not a recreational dive. The men are working on a heaving hull in the middle of the Pacific swells. They are suspended next to a dangling 20-ton steel component that could shift at any moment. Their tool is the underwater cutting torch. The process is slow and brutal. The divers must burn through the thick steel of the shaft while fighting the current. They are working against the clock of the weather and the fatigue of the metal. If the shaft breaks free before the cut is complete, it could take a diver with it. They succeed. The torch severs the final inch of steel. The rear section of the shaft, still attached to the propeller, slides free of the strut. It plummets into the abyss. The threat is gone. The divers surface. The engineers secure the remaining stump of the shaft from the inside to seal the tube. The Pennsylvania is now lighter. She is missing a screw, and she is still shipping water, but the leak is controlled. The journey resumes. She reaches the Puget Sound Navy Yard. The salvage mission is technically a success. The ship has been retrieved from the war zone, but as the engineers inspect the hull in Washington, the Navy is already rewriting her future. She will not be repaired for active duty. She has been selected for a new mission. She is going to be a target in an experiment that will make the torpedo hit look like a scratch. 2 nuclear detonations. That is the new standard of violence for the USS Pennsylvania. The torpedo hit in 1945 was a localized kinetic event. It punched a hole in the steel. The trials of 1946 are designed to test the total survivability of the vessel against the absolute release of energy. The ship that fought for 4 years to stay afloat is now anchored in the lagoon of Bikini Atoll to see if she can be vaporized. In July 1946, the United States Navy conducts Operation Crossroads. The first test is designated ABLE. It is an atmospheric airburst. The bomb detonates several hundred feet above the target fleet. The blast wave slaps the ocean and hammers the superstructures of the ships. The Pennsylvania is situated in the target array. The heat sears her paint, and the pressure wave bends her light steel fittings. But she does not sink, she does not burn, she remains essentially intact. 3 weeks later, the engineers reset the stage for Test Baker. This is the underwater detonation. The physics are entirely different. The bomb is suspended beneath the surface. When it detonates, it does not create a fireball in the sky. It creates a hydraulic hammer. The shockwave moves through the incompressible water at the speed of sound. It strikes the submerged hulls of the target ships like a solid physical blow. A massive column of water rises into the atmosphere. It lifts millions of tons of spray and coral debris. As this column collapses, it creates a base surge. A rolling wall of mist and radioactive sea spray expands outward across the lagoon. It swallows the fleet. The Pennsylvania is drenched in this lethal fog. Water lashes her decks and clings to every surface. When the mist clears, the Pennsylvania is still floating. She has survived the torpedo, she has survived the open ocean shaft failure, and now she has survived 2 atomic blasts. Physically, she appears defiant. She is one of the few ships in the target zone that has not capsized. But while her hydrostatic integrity is sound, her material future is over. She has been defeated by a microscopic enemy. The problem is contamination that will not let go. The fallout from Test Baker is not just dust that settles on a deck. It is radioactive material driven onto steel by seawater, spray, and the base surge. It soaks into paint, collects in seams, and works its way into rust and scale. Battleships are made of iron and iron rusts. That rough, porous surface becomes a trap. The Navy attempts to decontaminate the survivors. High-pressure water scours the decks. Harsh chemical washes follow. Wire brushes and manual scrubbing go after what will not rinse away. The results are limited. To drive levels down, crews would have to strip coatings and scale, and every abrasive step risks turning contaminated material into airborne dust. The Pennsylvania is dangerously contaminated. She cannot be safely manned for long periods. Towing her to a scrapyard and cutting her up is judged impractical and risky because of the contamination. She cannot be returned as a museum ship. She is structurally alive, but operationally condemned. The engineers tow her away from the test site to Kwajalein Atoll. They moor her in the lagoon and study her for 18 months. She becomes a floating laboratory for the long-term effects of radiation on naval architecture. But eventually, the data collection is complete. There is only one way to close the file on a ship that refuses to sink. The USS Pennsylvania sits at anchor in the lagoon of Kwajalein Atoll. She is a ghost ship. Her paint is peeling and her decks are silent. There is no crew to chip the rust or service the engines. The radiation sensors still click with a steady warning rhythm. She has survived the Imperial Japanese Navy and the physics of the atomic age. But she cannot survive the logistics of peace. The Navy has no use for a radioactive battleship. She is a liability. Maintaining her anchorage requires resources, and her contaminated hull presents a constant environmental risk to the lagoon. In 1948, the order is given to dispose of the vessel. This time there will be no enemy aircraft and no dramatic explosion. The end of the ship will be a controlled industrial procedure. On February 10, 1948, a small Navy party boards the vessel for the final time. They are not there to save her, they are there to prepare her for scuttling. A warship is designed with elaborate systems to keep the ocean out. But when a contaminated hulk becomes a liability, the Navy can also choose a deliberate sinking. Once preparations are complete, the ship is intentionally flooded and abandoned to the sea. The death of the Pennsylvania is slow and quiet. The water rises in the bilges. It fills the shaft alleys that had flooded violently 3 years earlier. It rises over the main bearings and extinguishes the dark, silent boilers. The stern begins to settle. The geometry of the sinking mirrors the damage she took off Okinawa. The stern goes down and the bow rises. But this time there are no damage control parties to fight the trim. The angle increases until the ship loses her stability. She slides backward. The water closes over the quarterdeck, then the turrets, and finally the tripod mast. The surface of the lagoon churns briefly as the air escapes from the internal voids. Then the water goes flat. The Pennsylvania does not stop at the bottom of the lagoon. She has been positioned over deep water. She descends into the dark until the last bubbles vanish and the sea closes above her. The exact resting place has not been publicly documented in detail, and no widely published survey has confirmed her condition on the seafloor. Far beyond reach, she remains unvisited and unverified. This is a fitting obscurity for a battleship built to close the brackets. She began her war in the shallow mud of Pearl Harbor, surrounded by burning oil and defeat. She ended it in the deep Pacific, having absorbed every punishment the enemy and her own creators could invent. She remains the only ship to witness the start of the war from the dry dock and the end of the war from the casualty list. She proved that a 30,000-ton machine could be broken by a torpedo, severed by a torch, and irradiated by a bomb, and still refused to sink until her own crew opened the gates. The ocean did not take the Pennsylvania was given to the ocean.